This video will show you how to calculate the pH of a salt solution. Okay, so the first thing we do is we realize that we are dealing with the salt. And so from this salt, we want to think about the ions that it is going to dissociate into. So we'll have sodium ions and we will have fluoride ions. Now, we know that alkaline metals have no acid-base properties in water, so the ion that we're concerned with is the fluoride ion. So the first thing that we do is we write the dissociation reaction for that ion in water. Has no protons to give, so it will gain a proton, and then we will get HF and the hydroxide ion concentration. One of the things that you can use as a clue is if a Ka or a Kb is given for the conjugate, that is what's going to form, and that ought to help you figure out which ion to pick. So here's our reaction. If we are following the same format that we did for acids and bases, we'll set up an ice chart. Water's a pure liquid, we're not including it. And then we're going to include the information that we know, which sodium fluoride is 0.30 molar, because this is a 1-to-1 molar ratio. So sodium ion would be 0.3 and fluoride ion is 0.3. Before the fluoride ion reacts with water, we have no HF and no hydroxide, so each of these are 0. Our reactant side will go down by X, our product side will go up by X, so we have 0.3 minus X, X, and X. Okay, the next thing we're going to do is we are going to, if you look here, going to write a Kb. Now, we don't have a value for Kb, but we do have a value for Ka. And if you remember from the Ka-Kb video, did I do one? I don't remember, so maybe it's from class. The relationship between Ka and Kb is that Kw equals Ka times Kb. So if I want Kb, I am basically taking Kw and dividing it by Ka. So to get my Kb, it's going to be 1 times 10 to the negative 14th divided by my Ka. And these two are conjugates of each other, so it's okay to do this. 7.2 times 10 to the negative 4th. That will be equal to the concentration of my products. They're both the same, so that's x squared divided by 0.3 minus x. So now I need to do some math. All right, so when I do this, I get 1.389 times 10 to the negative 11th. That equals x squared. Because Kb times 100 is still much less than this, I can go ahead and approximate. So it's x squared divided by 3. This is like it's over 1. So I'm going to take 1.389 times 10 to the negative 11th times 0.3. That gives me 4.167 times 10 to the negative 12th. That equals x squared. If I take the square root of both sides, let's go back to yellow. X will equal, let's look at sig figs. I'm going to do 2.0 times 10 to the negative 6. That tells me the concentration of the hydroxide ion. So now what I want to do is I can either turn around and calculate H+, which since I'm thinking about that, I'm going to go ahead and do that. Let me erase some of this because I don't really need it. All right, so Kw is equal to H+ concentration times hydroxide ion concentration. So if I want hydrogen ion concentration, I will do 1 times 10 to the negative 14th divided by my hydroxide ion concentration, which is 2 times 10 to the negative 6. So that gives me 4.9 times 10 to the negative 9th. And then when I want to find pH, I will do negative log of 4.9 times 10 to the negative 9th, which will give me, okay, 2 sig figs here, so 2 numbers after the decimal, 8.31 as a pH. Okay, now stop and ask yourself, does that make sense? Basic salt, basic pH, yes it does. Let's do another example. Okay, so here we're going to calculate the pH of a 0.10 molar ammonium chloride solution. So the first thing we have to do is recognize that this is a salt. We must divide it into its ions. So we will get ammonium ions and chloride ions. Water's also there. We're just kind of remembering that in the back of our head. From what we talked about earlier, we know that the chloride ion is the conjugate base of a strong acid, so it has no acid-base properties in water. So we are going to select the ammonium ion. We will write the ammonium ion plus water, and that will give us ammonia and hydronium. Now, I know that partly because the Kb for ammonia is given, but I also know if I have ammonium gain a proton, I get something I haven't really seen before, so more than likely that's not going to form. But if ammonium donates a proton, we get ammonia, and we're pretty familiar with that. So hydronium ion forms, which tells me I'm going to need a Ka. And then I'm going to substitute what I know. I know that ammonium is 0.10 molar. I know that because it's a 1-to-1 molar ratio. So if the whole thing is 0.1, ammonium is 0.10, and chloride is 0.10. Both of these ions are 0 to begin. So when ammonium starts reacting with water, we'll go down by X. Ammonia and hydronium will go up by X. So I get 0.10 minus X, X, and X. All right, so I need a Ka. Ka is equal to, I'm not given one, so I'm going to use Kw equals Ka times Kb, and I want Ka, so I'm going to do Kw divided by Kb. So 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. That is going to equal, let me go ahead and calculate that. That will give us I think it's like 5.56, so I'm just going to do 5.6 times 10 to the negative 10th. That equals concentration of products, X squared, divided by 0.10 minus X. Okay, if I take Ka times 100, much, much smaller than my original concentration, so it's okay to approximate. This is like it's over 1, so I'm going to take 5.6 times 10 to the negative 10th times 0.1, and I get 5.6 times 10 to the negative 11th. That equals X squared. I'm going to take the square root. I will get X equals 7.48 times 10 to the negative 6. That's concentration of hydronium. That is concentration of ammonia. If I wanted to know concentration of ammonium, I would do 0.1 minus that number, 0.1 minus that answer, and I would get 0.099999, which really is still 0.1, so you know your approximation is valid. Okay, so the goal is to find pH. This is my hydrogen ion concentration. So what I can do, I'm going to remove this, so I've got room to write pH. is going to equal the negative log of 7 points, basically 7.5 times 10 to the negative 6. So our pH, negative log of 7.5 times 10 to the negative 6, gives us 5.2 sig figs, 2 numbers past the decimal, 5.12. I have an acidic salt, acidic pH. That makes sense. Okay, so what do we do if we have one of those freaky complex ion ones? So let's say we have one that's a 0.010 molar aluminum chloride solution, and we are given a Ka for, this would be, oh, this is going to make me think. This would be hexa aqua aluminum 3 ion. We'll teach you how to do those later. That's the Ka for that. Okay, so the first thing we do, like we were doing before, we divide it. The chloride ion has no acid-base properties in water. It is the conjugate base of a strong acid, so it's a weaker base than water, so we want the aluminum ion. We know that that aluminum ion, when it reacts in water, is going to form this lovely thing. And that will react with water. So that will form this, which would be penta aqua hydroxy aluminum 2 ion and the hydronium ion. Okay, hydronium ion means that this salt is acidic, so we need to end up with a pH less than 7 or we've done something wrong. Go ahead and set up our ice chart. I don't think you'll have to do one this challenging on the AP exam, but it's good for you to see an example. So I'm going to fill in my given. This ion is 0.010 molar. Both of these have 0 to start. This will go down by X. Each of these will go up by X. So we get X, X, and 0.1010 minus X. These are going up by X because both of these are 0. So I need a Ka, which thank goodness I have. So I'm going to go ahead and write the expression just because we haven't done that in a little while. So this is going to be the concentration of the penta aqua hydroxy aluminum 2. Whoops, that should be on the inside, sorry. Aluminum 2 ion times the hydronium ion divided by the hexa aqua aluminum 3 ion. So we are going to substitute. We will have, I'm going to erase up above it. No, I'm not, because then we can't see what we're doing. Okay, so I'm going to have 1.4 times 10 to the negative 5th equals x squared divided by 0.010 minus x. If I multiply this by 100, I am going to have I gotta check, 1, 2, 3. That is still smaller than that, so it's okay if we approximate. So if I take 1.4 times 10, 1.4 times 10 to the negative 5th times 0.010, that will give us, let me change colors, purple. 1.4 times 10 to the negative 7th equals x squared. If I do the square root, my x is 3.74 times 10 to the negative 4th. That tells me my hydronium ion concentration. So to get pH, I can do pH equals negative log of 3.74 times 10 to the negative fourth. When I do that, I get, all right, I gotta think sig figs. 2 sig figs, 2 digits after the decimal, so I get 3.43, which is an acidic pH. We're done.